I've got two more linear regression problems for you. You're probably getting tired of them by now, but I wanted to make sure you had enough examples so that you are able to handle anything that we throw at you. Let's linearize this data. Check and make sure everything is on the increase. That column is increasing, that column is increasing. Check. Now we check for proportionality or linearity. 0.25 to 0.5, that's a doubling. 0.3 to whoa, that's not a doubling. That's way more than a doubling. So let's check one more. How about from 0.5 to 1 is a doubling? 1.2 to 4 yow. That is not a doubling. That's way more than a doubling. Who's having trouble? Who's lagging behind in this foot race? It looks to me like time is lagging behind. When we double time, the displacement goes way more than doubling. What we need to do is we need to help time out. So time usually, isn't it right? Lowercase t often, displacement, any number of variables we could give it there. Let's call it d, but we're going to square the time column because time needs some help keeping up. So we square the variable, we square the unit, and here we go. So when we square those, 0.0625, 0.25, 0.5625, 1, 1.5625, and 2.25. As with all of these videos, feel free to stop them at any time and do these on your own, but I'm not going to sit here and just wait for you to do it on your own. You can stop the video and do it at your leisure. I've changed this column, so I'm done with it now. I put a little cross through it there so that I'm not tempted to put it into my calculator. Let's check for proportionality now. Here we've got 0.3 to 1.2. That's about a factor of 4. How about this? 0.06. If I multiply that by a factor of 4, it's going to give me about 0.24. Yep, that looks good. Let's do one more. How about 1.2 to about 4.9? That's about a factor of 4. 0.25 to 1, that's about a factor of 4. Looks good. All right, the next step is to decide which ones should be your x values and which ones should be your y values. Rise over run. And the way we decide rise over run is we look at the units and we say, if this one were on top and that one were on the bottom, would we get a unit that we would recognize? And that answer is yes. These are the rise values. In other words, those are our y's. And if these are our run values, our x's, rise over run would give you meters per second squared, and that's the unit for acceleration, isn't it? Perhaps you recognize that. So when we type this into our calculator, these are going to be our x values, and the displacements are going to be the y values. As if on cue, there's my calculator. Go into stat mode, go to edit. You can see I've already put in the values. The x values in the L1 column, the y values in the L2 column. Now let's quit by hitting second and quit. Don't hit clear. I've done that a few times. That's not what you want to do. You want to quit. Now you want to go back into stat, and now we're going to calculate, and we're going to toggle down to linear regression because we are linearizing. I've arranged all the variables in the columns that I want. So I'm just going to hit enter a few times, and this is the result we get here. Y is equal to 4.93x minus 0.011. But we don't want to leave our variables as generic x and y. We want to use the variables that we have in our problem. And our y values have the variable d. And our x values have the variable t squared. So there you go. Very often, I've said this several times now, this intercept will be a very small number in comparison to the rest of this, which is not always the case, but let's say it is here. So we can pretty much approximate this equation as 4.93 t squared. All right, then it might ask you a question about this data. And we need to associate this equation with some physics equation. Well, you might remember that there's a physics equation that looks kind of like this. V initial times time plus 1/2 acceleration times time squared. And do these two equations relate to each other? Well, that looks a lot like that. V naught, perhaps we're told in the problem that this thing started from rest. Well, if it started from rest, then V naught is 0. And that means that those two terms are the same thing. So it could ask you, hey, what is the acceleration of this mass? Well, we would need to equate these two, right? And if that much t squared is equal to that much t squared, then it looks to me that that must be true. Isn't that right? The t squareds are the same on both sides. Therefore, 1/2 a is equal to that. And therefore, the acceleration would be twice that, whatever that comes out to be. I'll go ahead and type it in, 9.86. 9.86. Looks to me like something's in free fall. All right. So just be careful whenever you are asked the next question. The answer to the next question is not always the slope, 4.93. Sometimes there is a multiple in there that needs to be accounted for. In any case, it's this boxed in thing here on the left side that we really want to make sure that you get out of these videos. This other stuff here on the right, that's just extra kind of application stuff that your teacher, I'm sure, will go through with you as you work through things.